All right, hi everybody again. Sorry I had to stop that previous recording because I got interrupted, but we'll just pick up where we left off. Force equals mass times, with an S, times acceleration. So let's just define our terms here. What is mass? So mass is the amount of matter in a body. I think you all kind of have a good idea. This is a little different from weight. We'll come back to weight later. Mass is just kind of that physical stuff in a body, in a planet, in a moon, right? Newton's first law and Galileo says that if you have mass, it resists changes in motion. That was our definition of inertia. Galileo's relationship and Newton's first law, right? Object at rest is going to resist a change in motion and it wants to stay at rest. An object in constant motion resists a change in that motion, okay? I got my little thingy in the wrong spot here. Okay, here we go. Okay, so let's do some examples here. For a specific object, right, the mass isn't changing, it's the same object. If you apply a greater force, that means that you're gonna have a greater acceleration. There's a direct relationship between the force and the acceleration for the same object. You push something harder, it accelerates faster, right? Here's this lady pushing this same object. She pushes it with a smaller force, you have a smaller acceleration. She pushes it with a bigger force, it's gonna speed up faster. It's gonna have a faster change in its motion. It's gonna have more acceleration, okay? However, if you can think about this same relationship in a different way, if you exert the same force, so the same force, this time you're pushing with the same amount of force, but you're pushing on different masses, then objects with more mass will accelerate less. So for this one, we compare this first picture, right? Pushing 100 kilograms with this little f force. Compare that to picture C. You're pushing twice the mass, a much bigger object with the same little f force. And look, your little a got small. It's a teensy tiny acceleration. You can try this at home. You may not have a big block on a cart, but maybe you have a rolly chair or something else, a skateboard, something that zooms across the floor. You can try pushing it with different forces. You can try putting something heavy on it, have, your brother or something sit on it, and see how that changes. But this is the idea. So I'm not going to have you put numbers in, but I want you to understand greater force gives you a greater acceleration if the mass stays the same. For different masses, you have the same force, you get a different acceleration. Okay, so I want you to understand how that works. Physically, try it out. Right? If I was in class, I would actually do it for you, but you need to just do it at home this time. Okay. All right. So here's your question. An unbalanced force must be acting when? Go back, think about Newton's second law. What does an unbalanced force cause? And then what was our example? Think about the car. What does that mean? Okay, I'm going to pause here for just a moment and let you think about it. Try to pause the video, answer it. I'm not going to pause that long. So an unbalanced force causes acceleration. Right, that's Newton's second law. If you have a force on a mass, it's going to accelerate. So an unbalanced force causes acceleration. So A must be correct. But what is acceleration? Remember our car? For a car to accelerate, it's a change in speed and or direction, right? It was the gas, the brake, and the steering wheel. So let's go through our other choices. Changes direction but not speed, that's the steering wheel, that's acceleration. Changes speed but not direction, that's the gas or the brake, that's acceleration. Changes speed and direction, yes, also acceleration. So that leaves us with all of the above as the correct answer there. So those are Newton's first and second law, inertia and force related to acceleration. Newton's third law then is that forces occur in what we call action-reaction pairs. Action-reaction pairs. For every action, y'all might know this one too, for every action, there is an equal and opposite reaction. Again, I'm going to add a few special words here. There is an equal size, and opposite direction reaction. Equal size and opposite direction reaction. What does that mean? Okay, that means that there's the same amount of force, so equal size, same amount, but it's opposite direction. It goes in the other way. This applies to all forces. We don't think about some forces, especially gravity, this way, but it's true. All forces have a pair, including gravity. So let's do the gravity example because we're trying to think about orbits and we're trying to think about things like the moon and the earth and the sun. Right, so let's do that example. The moon exerts an equal size force on Earth. So here's the little moon exerting a force on Earth. That is equal to the force the Earth exerts on the moon. The Earth exerts a force on the moon. Those two are equal. You see, we just have one F here. So this is the same as that. How can that be? Because the Earth is a lot bigger than the moon. So how can something bigger exert the same force? It's because both masses matter. And we're going to get to that and we're going to talk about that soon. But it's equal, right? That's what I want you to take away right now. It's equal, but look, it's opposite. The Earth pulls on the moon and the moon pulls on the Earth, but they're in opposite directions. Equal force, opposite directions. Okay. This, by the way, is how you can launch a rocket. In this case, it's not equal. You have to overcome gravity. So if you want your rocket to go anywhere, you have to have more lift than gravity pulling down. But it's a good example of a pair, right? We don't blast off unless we overcome that pair, that action-reaction pair. Okay. Got one more poll, and then also I want you to watch a couple of videos, and I'll show you that in a second. Okay. So here's another one. This is about Newton's third law. Your weight, and we're going to talk more about weight soon. Your weight is the force of Earth on you, the force due to gravity on you. If you weigh 60 pounds, pounds is a force unit. The force of you on Earth is what? Okay. Earth, right, here's Earth, here's you. Earth is pulling on you with 60 pounds of force. How much are you pulling back on the Earth? We want to say that we're not pulling on Earth, but we are. Remember, equal size, opposite direction. So if it's equal size, There's only one right answer. Equal size. So why doesn't the Earth move? Every time you take a step, why doesn't the Earth follow you? Because you're teeny tiny. In this picture, I drew you as big, but the Earth is so, so huge that it doesn't even notice your little 60 pounds. Okay? But there is an equal and opposite reaction there. So those are the notes for Newton's laws. I'd like for you to as well watch a few videos. I'm going to add these videos that I made to this playlist. There's this one that just on Newton's 3 laws that just quickly goes over all 3, but gives you an example of a bicycle. And then if you're confused about this whole equal and opposite thing, how can you be pulling on the Earth with the same force that's pulling on you? Watch this best film on Newton's 3rd law ever. Okay, so I will leave those for you for resources. You also need to complete the activity, the lecture, or the tutorial activity in your workbook. See my email for complete instructions. See you later.